I'm Junhui from City University of Hong Kong. So today I'm pleased to share you our recent works on deep modeling of 3D point cloud data. Yeah. So yeah, first we use several pages to show you the background. So for point cloud, I think all of you are familiar with this kind of data. It's a kind of a raw data or to represent the 3D geometry, right? So it's a for 3D point cloud, actually it's a set of unstructured 3D points. Okay. So defined by the 3D coordinates, yes, it's X, Y, Z, and indicate the 3D location, yeah, and also additional attribute information like the color information and the number information. So this kind of data has been used in various applications like the autonomous driving, immersive telepresence, and the digital, the culture heritage, and yeah, a lot of applications. Also nowadays we can obtain this kind of data, yeah, relatively easily. Like you can use a multi-view based devices, the structured light devices of the laser or the millimeter wave based devices. Okay, so yeah, so we can obtain this kind of data relatively easy compared with the previous years. Okay, so this page two we can compare the difference between the 2D images because it's a commonly used data, yeah, and the difference. So if we can under the difference between these two kinds of data, so we can model the 3D point cloud data, yeah, better. So this is the left side. This is the 2D image. Is actually it's a illumination information, right? So it's a set of pixels regularly sampled on the Euclidean space. Yeah, it's a plane. But for 3D point cloud, it's a geometry information. As I mentioned earlier, it's a 3D coordinates, irregular sampled on the non-Euclidean space. It's a surface. Okay. So more specifically, so for the images, the image it can be sort of a sort of as a set of five-dimensional points, regularly distributed. So it's a signal is the RGB values, and the index is the pixel index. We use the UV indicated the index. If we want to use the deep learning, it's a convolutional neural network to process the 2D images. We process the signals RGB, and we can find out the neighbors. Okay, the neighboring pixel use the index, so it's quite convenient, right? But for point cloud, so as I mentioned, it's a geometry information, a set of 3D coordinates defined by the X, Y, Z. Okay, so for this kind of information used, we process the data. Yeah, it's the signal. Yeah, to be processed. Also, we use this data to this information to find the neighboring points, right? So to aggregate the local information. Yeah, so this is a fundamental difference between these two kind of data. Also, I call this data this kind of this difference as the unstructured property. Okay, also this unstructured properties challenge the development of deep modeling of 3D point clouds. That's how to design the downstream algorithm. Okay, it's more challenging. Okay, more difficult than the convolutional neural network. Okay. Also, this irregular unstructured data pose challenge to design the loss function. It's for the image later we'll introduce. For image, we can use the pixel-wise, right? Like the PSR, the MSE, or other kinds of L1 loss. But for point cloud, there's no correspondence. Okay, as I mentioned earlier, there's no index, no a predefined structure for point cloud. Okay. Yeah, so for deep learning, for convolutional neural networks have been widely used to achieve great success to process the 2D image, right? So this is the basically analogy to the convolutional neural network. We can design the 3D point cloud data, the deep architecture for modeling 3D point cloud data, like the commonly used modules. Okay, in convolutional neural network, it's like the convolution, right? So to aggregate the local information and improve the pixel from the pixel domain to the feature domain, right? Also the pooling operation, deconvolution, to increase the dimension, also the loss function. So similar to the CNN, we can design a deep architecture for 3D point cloud, right? Like so as I mentioned earlier, the points are irregularly distributed, so we can apply the CNN. Okay, so in other words, fundamentally, it's a difficulty to. There's no predefined structure. Okay, so how to define the neighbors? Okay, it's a challenging issue. So here we can use MLP to improve the data from the spatial domain to the feature domain. Also, we can aggregate the neighboring points to aggregate the local information. Okay. Also, we need the permutation invariant aggregation. For the pooling, it's a sampling, right? It's a sampling like the random sampling or farthest point sampling or other kinds of other advanced sampling method. For the deconvolution, you can simply you can use the duplication or interpolation. Okay, so for the loss function, the two commonly used loss functions, the transfer distance and the Earth mover distance, right? So this is the how to design a deep architecture for modeling 3D point clouds, right? So over the past year, since the pioneering net work is a point net, right? So there are a number of deep architecture. So here we focus on the point-based framework. That is, we process the network. The network consumes the points. Okay, consume points directly without the pre-processing, like the projection virtualization, right? So here, this is some representative deep architecture for modeling 3D point cloud data directly, okay, without the pre-processing. Okay, so here I summarize the major challenge and the difficulties faced by this pipeline. Like the first one is they are computationally and memory expensive. So it's it's a time consuming or memory consuming because due to the following operations like the neighboring search, you can use a KNN or ball query or other to find the neighbors, or also the downsampling like the FPS, right? So we know this operation can be implemented in parallel, right? Also upscaling is interpolation. So these operations will produce many intermediate data, also resulting in it's memory consuming and the computationally expensive. Okay. So this is a statistic about the memory consumption and the inference time. Okay, so like the PointNet plus DGC and the point transformer, right? So this the x horizontal axis is the number of points. Okay, so the vertical is the time and the memory cost. So here you can observe if we feed to about 20,000 points, the inference time go up to more than 1 second. Okay, also the memory. Okay, the memory is go more than 16 gigabytes. Okay. So the second issue is the representation capability of the point-based feature aggregation is sufficient. Okay, so generally we can formulate the aggregation feature aggregation of a point-based is MLP plus pooling. Pooling it can be as a simple permutation invariant pooling or advanced attention-based pooling. Okay, so so the fundamental issue is there is no unified order. Okay, so it results in the inadequate representation capability of the feature aggregation operators. Okay. Also, the third limitation is the distance metric. Okay, it's the either time consuming. Okay, for a large scale they are not effective. Like for EMD, okay, it's effective but it's time consuming. Okay, but for the CD, for the chamfer distance, it's efficient but not effective. Okay. So here we in the past years we focus on these issues to address these issues. So here we address this issue from three perspectives. So the first it's about the we propose, as I mentioned earlier, there is no predefined structure for the point cloud data, right? So here we can use a structured representation. Yeah, so we propose a represent the 3D point cloud as 2D images for point cloud sequence as 2D videos. Also, we propose then to augment the learning process. Okay, use a distillation or other kind of a 2D to 3D translation. Also, we propose the efficient, yield effective distance metric. So finally, we will conclude this presentation. So first, let's go to the first part. Is the structured representation of a point cloud data. Okay, so here we propose to represent the 3D point cloud, each 3D point cloud as a 2D image. Okay, so here this is this figure to illustrate the process. I think this animation to show you. So for RGB image, right, there are 3 channels, RGB values. So here we reorganize. So given a point cloud, we organize each point as a pixel. So the 3 channels correspond to the X, Y, Z dimension. It's the idea is similar to the geometry, but it's a difference. Okay, because this reorganization is not a parameter relation. Later we'll introduce the parameter relation. So this is a reorganization in the sense of Euclidean distance. We just want to reorganize a point into the regular grid such that the neighboring pixel, okay, the neighboring points, okay, are still close to each other in the 2D domain. Okay, so we call it the spatial smoothness. Okay, so the neighboring spatial points are distributed at the adjacent pixel location. Okay, each RGB value, okay, each pixel, okay, correspond to the 3 coordinate of point. So if we have such a representation, regular representation, we can directly process this image, okay, use a convolutional neural network. So in other words, it's equivalent to assigning a 2D coordinate, okay, a 2D coordinate to each point, right? So if the 2D coordinate are regularly, it's a 2D regular grid, then we can obtain the image, the 2D array, right? It's a 2D array. So this is more examples. So this is the basic idea. Okay, so to reorganize, okay, to reorganize the points into the pixels. Okay, in other words, to assign a regular 2D coordinate, okay, to each pixel. Okay, we can decouple the signals and the index, right? We can decouple the signal and the index. Okay. So how to achieve? So here we propose the self-supervised learning pipeline. Okay, so we can't design the supervised because no ground truth. Okay, no ground truth available. So here, simply we basically we use a self-supervised learning process. That is, the intuition is if we have the smooth prior. The intuition is the smooth prior. If the input is a 2D, it's a small signal. Okay, and also plus the spectral bias of neural networks. Okay, the output should be smooth. Okay, so the smooth input and with the spectral bias of a neural network, that is tend to learn the low frequency. Okay, low frequency of the data. Okay, so the output will be a small signal. Okay, also we add this additional regularization items. Okay, so like the smooth regularization to the output. Okay, so that is the central pixel should be tend to be the average of a neighboring pixel, right? So the smooth regularization and also the geometry regulation, we can use the use the back propagation because this is a 2D to 3D mapping, right? So we can use the back propagation of this neural network to obtain a differential geometry attribute of the point cloud, like the normal. Okay, the normal consistent, right? So this is the basic idea. Okay, so here we evaluate the effectiveness of such a representation, okay, on the various applications. Okay, so here this like the point cloud classification. You can use the design a 2D convolutional neural network to classify that because we have represented each point cloud as an image, right? Also, you can process the large scale point large scale point cloud data. So this is classification, also the point cloud upsampling, also self-reconstruction. Okay, so we demonstrated the advantage, okay, of this unified representation, okay, or generic representation. Okay. Yeah, so this is to represent each static 3D point cloud. Okay, so here if we have a 3D point cloud sequence, okay, yeah, so intuitively we can represent it as a 2D videos, right? So each point cloud as a frame. Okay, so we put all frames together, we obtain a video. So here, so the input is a 3D point cloud sequence without a correspondence. That is the over the in the temporal domain, we don't know which point corresponds to which point. Okay. So the output is a 2D video with a spatial smoothness and also the temporal consistency. That is the temporal consistency referred to the pixels at in different frames, the same location correspond to correspond to the semantically similar. Okay. So this is so here this column indicates the correspondence, okay, over the time domain. Okay. So yeah, similar to the previous one. So the basic idea is the first we can represent the first frame, the first frame as an image. Okay. So later we will align the following frames. Okay, the following point cloud frames with the first one. Okay, to learn it's similar to learning the same flow. Okay, over through optimization. Okay, so if to learn the offset, then we can achieve the spatial smoothness and also the temporal consistency. In this way, we can obtain the a 2D videos. Okay, so here this is some applications to verify the effectiveness of this representation, like the 3D action recognition. So here, that is a point cloud-based data, okay, to recognize the action. Okay. Also, the temporal interpolation is a counterpart of the 2D frame interpolation, right? So given a sequence with sparse sampling the sequence, okay, in the time domain. So we interpolate the intermediate frames. Okay. Also, like the 3D point cloud sequence compression. Okay, you can use a mature 2D video encoder codec to compress the 2D the resulting videos. Okay, so here you can show this figure demonstrates a significant advantage of this representation. Okay, so it can be credited to the advanced the well developed 2D video codec. Okay. Yeah, we can go further. So as I mentioned earlier in the previous page, so we reorganize the idea, the resulting image is similar to the concept of geometry image, right? Proposed in 2000, right? So about more than 20 years ago, it's based on the parameter relation, right? Mesh parameter relation. But for the previous two representations, so we reorganize the point in the sense of a Euclidean distance. So it's just the neighboring points in 3D space to be are located in the adjacent grid. Okay, in the sense of a Euclidean distance. But here, so for the original concept of geometry image under the mass obtained via the mass parameter relation, right, to find a bijective mapping, okay, to minimize the angle or area distortion. But there's some limitations, okay. It limited flexible with the input the mesh, okay. It requires a well-behaved mesh, okay. So like the triangle should be regularly distributed, okay. Also, if it's a closed model, we have to find out a good cutting seam, right? So the question is, can we parameterize a point cloud without connectivity? So that is given a point, given a point cloud, can we map the points to 2D domain, okay, with the the physical meaning. Okay, so here this yeah, the answer is yes, we can. So here this is given a point cloud, right? Given a point cloud, so this is a 2D mapping. Okay, so this is a 2D mapping. So here we put the checkbox to show you the distortion. Okay, to show the distortion. Also here the last row, the bottom row to show you the green line. So the green line is the cutting seams learned by the algorithm. Okay, learned by the algorithm automatically. Okay. So the result is quite impressive. Okay, use an actually this is the unsupervised or self-supervised method. We don't know the ground truth parameterization. Okay, so how to achieve the parameterization of point cloud without connectivity information? Yeah, so the pipeline is a self-supervised learning process. Okay, and the bidirectional cycle manner. Okay, and also the we can achieve a smooth parameterization. Okay, also flexible input. Okay, so here's a basic idea that this is a given point cloud, right? So here we want to obtain the because we only have this point cloud, right? So we can design the inverse process is from the 2D to 3D mapping. Okay, so here we call it the folding module. Okay, so first we define the 2D regular grid, and this is a deformation module. Okay, to learn the offset to the regular distributed points, and then we will learn folding. This is via this folding module. Okay, to map the 2D to from the 2D domain to the 3D domain, and this process is supervised with the given point cloud. But in practice, we want to obtain the 3D to 2D mapping, right? So here we can add the cycle process. Okay, so we can add the unfolding module. Okay, we can add the unfolding module to unfold this 3D point cloud to 2D 2D domain. Also, we can use the loss. Okay, but this module, this branch is we only use a given point cloud to supervise the learning, but we don't feed the point cloud to the network. But in practice, we can feed the model, the point cloud to the network, right? Then we will add the following branch. So here, given the point cloud, we still copy the unfolding module. So here, these two modules share the same network parameters. Okay, so here we obtain this is a 2D. Then also we learn add the folding module. Okay, to fold this one to point cloud and add the L1 loss. Okay, because we know the correspondence. Okay, under this module, under this branch. Okay, so in other words, the following branch can be thought of as a regularization. Okay, as a regularization, because in practice we know the 3D point cloud, right? We want to feed the 3D point cloud to the network instead of using the point cloud as a supervision is somewhat weak, right? So if we can feed the network the point cloud to the module, okay, directly, then we can learn the parameterization better. Okay, so this is the basic idea. Yeah, so also we add the conformal regularization to the folding module. Okay. Yeah, so this is what's the time now? Yeah, we still have yeah, so this is a more result and Alexa. So here you can observe the green lines, the learned cutting seams. Okay. Also, we compare with the slim, the mesh-based parameterization. Okay, so this is some quantitative result. Okay, so this is the open surface. Okay, yeah. So this is the first part. We want to represent give a define a structure representation. Okay, to boost the deep modeling of a 3D point cloud. The second part is we can augment the learning process. Okay, we can augment the learning process. So here we use a multi-view image to 3D point cloud distillation and a 3D point cloud 2D representation translation, also the cross model information interchange. So in the following, I give you more details. As I mentioned earlier, so the challenge and limitation faced by the previous point-based deep architecture is so the first one, so like in this pipeline, okay. So if it's a self-supervised learning, right? So the encoder and the decoder. Okay, if we process the point directly, so we need a decoder, right? Because if we decode the point directly, so yeah, so use the MLP. Okay, it's difficult to handle large scale point cloud, but because the output layer, the last layer is depends on the number of points, right? So it's a so the number of the parameters will be huge, okay, of the decoder. So it's difficult to handle large scale point cloud data. Also, is a insufficient capability of a distance metric. So here for self-supervised, we need a metric to measure the discrepancy between the input and output, right? So here for the CD and the EMD, so it's a either ineffective or ineffective, right? Inefficient. Okay. Also, it's have limited feature representation ability due to the unstructured character. So in the other kinds of tasks, right? Applications. Okay. So here we augment the learning process. Okay, we augment the learning process. So the first one is we can project the 3D point cloud. Okay, we can. So this is the distillation pipeline. Okay, so given the point cloud, so this is the point encoder. Okay, the point encoder. So we obtain a point-wise embedding the feature. So this is the visibility aware feature projection. So it's based on that, when we project a 3D point cloud along a typical perspective. So some points are invisible, right? Invisible. So if we know the camera pose, we can detect, we know which points are invisible, right? So this is a visible aware feature projection of pooling. Okay. Also, so here we render the point cloud into the multiple images. Okay. And so this is a 2D image. Although the 2D image, if we render the point cloud into 2D image, we will miss some 3D geometry. But for the 2D image, it has a regular structure, right? So we can use a CNN to extract features to obtain the feature embeddings. Okay. So here, this is a teacher network. So we can align the image feature and the point feature. So this is after the pooling. Okay, the visibility aware pooling. So we can align the image feature and the point features. Okay, so after the training, so this is the point encoder. Okay, point encoder. Okay. So in this way, so we augmented the decoder. Okay, just align a feature. Okay, so this is also known as a distillation, right? So here, this is some experiments to verify so here, like the pointer can be point net plus DGCN or CurveNet, right? So we can, under this training process, we can improve the classification, the part segmentation. Okay. Yeah, so in the paper, there are more applications. Okay. So the second one to augment is under the self-supervised learning process, under the self-supervised training. Okay, we want to pre-train a point-based encoder. Okay, so different from the distillation. So here we do the translation. Okay, so here this is still the point-based encoder, right? Point-based encoder. Also, we learn a view-specific pooling. Okay, so that is given a virtual camera pose. Okay, this model to learn which point should be visible, which part is invisible. Yeah, so we learn the visibility instead of to detect the visibility directly. Also, we can do it. Okay, use the algorithm. Okay, but we didn't use the detection using the traditional method, but we learn this process. It can augment the ability of the network. But instead of decoding the point cloud, we decode the 2D representation, like the depth map, the silhouette map, and the contour. Okay, actually, this is also geometry representation, but in the 2D domain. Okay, but in the 2D domain. Okay, it's not a color image, it's not an RGB image. Okay, the depth image, the silhouette and map, and also the contour map. Okay, So, they are still geometry information, but in the 2D domain, also we can use the L1 or L2 loss or cross entropy to measure. It's a strong supervision. Okay, it will be a strong supervision. Also, the 2D CN, it will be more efficient. Okay, it will be more efficient compared with the MLP-based decoder. Okay. So here, this is some result, and like in the semantic segmentation and classification. Yeah. So here, in the paper, there are more result. Okay. The third one is we use the augmentation in the object detection, 3D object cross model object detection. So here, this is for the cross model 3D object detection. We have the RGB image, also the point cloud. We want to detect the object. Okay, obtain the 3D bounding box. Okay. So this is commonly the image to point projection. Okay, the image to point projection, it can decorate the point cloud with the image features, right? So this is commonly used to map the point features to a point cloud feature, okay, to enrich the point cloud features. But here we do the inverse mapping. It's a point to image mapping. Okay, we map the point cloud data. We map the point cloud feature to the image domain. Also, we use auxiliary supervision task like the semantic segmentation and the NLC map estimation. The NLC is the normalized local coordinate map estimation. So it's a somewhat strong supervision in the 2D domain. So we expect this kind of information will be augment the 3D backbone, the ability of a 3D backbone via back propagation. Okay, the information will transmit to the 3D backbone. Okay, via this bridge. Okay, so in this way, can enhance the capability of a 3D backbone. It's a point-based backbone. Okay, it's a point-based backbone. Yeah, so here actually this result demonstrates it's indeed boosts the capability of the 3D backbone. Okay, so here this is a single model if we only consider point to pixel. So this is a pixel to point. Okay, so this one, if you consider the point to pixel and also only consider this is a single model, only the 3D backbone. Okay, so we can increase the it's indeed increase the capability of a 3D backbone. Yeah, also this is to demonstrate that we need a auxiliary. We need the auxiliary task. Okay, so the supervision information will be back propagated via the bridge, the point to image projection. Yeah, so the third part is the distance metric. Okay, the distance metric, as I mentioned earlier. So yeah, actually for the distance metric, yeah, it's very important. Okay, if the supervision is not strong enough, okay, so it will weaken compromise the capability of the network, right? Yeah, so here let's record the image for the 2D image. How can we produce the difference, the discrepancy between two images? So here the blue dot indicates the location. Okay, so actually the image it can be thought of as the signal that defined over the 2D grids, right? So like this one. So this is the for image one. So UV is the coordinate, right? So F is the RGB value, So then we can calculate the difference. Okay, the difference between the corresponding pixels. Okay, indicated by the same location, the UV coordinate. But for point cloud, as I mentioned, there's no correspondence. Okay, there's no correspondence. Okay, so yeah, if there's no correspondence, okay, so the intuitive idea, we can find out the correspondence. Okay, like the Earth mover distance and the chamfer distance. Okay, so we can find out which point correspond to which point, right? So for EMD is a bijective mapping. Okay, one-to-one mapping, but for CD it can be one to more. Okay, So, but for EMD and CD, it's either ineffective or inefficient. Okay, for EMD it's inefficient, CD is ineffective. Okay, so here we propose the directional distance fields. Okay, inspired by the analogy to the 2D image. Okay, the loss function for 2D image. So this is the basic idea that we convert the 2D geometry model as a function of a common domain of a definition. Yeah, that's given a point cloud actually is a surface, right? So indicated the surface or object surface. We will define the surface, okay, define the 2D geometry as a function of a common domain. Okay, so here I use this figure to illustrate it. So like the black line is the 2D, it's the 2D surface, 3D surface, and so the blue dot is the domain of definition. Okay, the domain of definition. So the two geometry models share the same domain of definition. Okay, so we will define the surface as a function of a cube. Okay, as a function of a cube. So how to generate a cube? So that we just perturb each perturb the original points, okay, slightly. Okay, so the blue point is just surrounding the original surface. Okay, this is a cube. Then we will the next step we will define how to define the surface. It's similar to the unsigned distance function, right? So it we measure the distance, okay, q the distance to the surface, okay, to the surface directional distance. Okay, so this is a function we define the 3D geometry as a function of a q, okay, as a function q. So here those is the four-dimensional function. It's the distance and the direction. Okay, the distance and direction we call the directional distance. Okay, we call the directional distance. So in this way, you can compare given a two geometry, two 3D geometry model. That it can be a point cloud or 3D surface, right? It can be a point cloud 3D surface. So we can just compare the difference between the two functions. Okay, point by point, over each cube. Okay, over each cube. So this is a figure to show you how to approximate the distance from a cube to the surface. Okay, just use the if it's a surface, if it's a mesh model, okay, we can compute. If it's a point cloud, we can approximate use the neighboring point via the weighted combination. Okay. Yeah, we demonstrate that we conduct a number of applications to demonstrate the advantage of this metric. Okay, like this is the rigid registration, right, from the source point and the target point to length R and the T rotation matrix and the translation matrix. So here this is ours. So yeah, so with a good distance metric, okay, the registration accuracy can be improved significantly. Yeah. Also, this is the non-rigid registration. We also need a distance metric to measure the discrepancy between the deformed surface and the target surface, right? So this is the distance metric, okay, to measure the discrepancy between two geometry models. Okay. Yeah, so here we compared with the most recent the work. Okay, so the registration error. Okay, the registration error reduced significantly. Okay, so here this is some visual result, and also the human pose optimization. That is given a point cloud and also the template model. Okay, we can optimize the parametric model. Okay, so the parametric model, the skin, the multi-person linear model is just to optimize the parameter, to optimize the parameter to align the parametric model with the point cloud. Okay. Yeah. So this is under different distance metric. Okay. Yeah. So this is the sim flow estimation. Yeah. Also, we need a distance metric, right, to learn the offset. Okay. To learn the offset. Yeah. So a good distance metric can improve the accuracy, okay, significantly. Okay. Yeah, so yeah, so here let's so finally I conclude this presentation. So we have done to overcome the challenge associated with applying deep learning technique to model the 3D point cloud. Yeah, we address the limitation from a three perspective. So yeah, the first one, if there's no structure, okay, there's no structure, we define a structure, okay, to improve the efficiency and save memory, facilitate the design process, and it also bring performance gain because you can use the matured 2D learning techniques. Okay, also it facilitates the designing process. Okay, because you can process the point cloud like the processing a 2D image, right? Also, we leverage the 2D representation to augment the learning process. Okay, it's a like the 2D representation is you can use to avoid the limitation of the MLP, and also we have a 2D representation. It has a structured representation. You can use strong supervision, like the L1 loss or other. Yeah, also use the efficient yield effective distance metric. Okay. Yeah, so here we also conduct other geometry processing works like the compression, the 3D point cloud generation, and also surface reconstruction, and also sampling. Okay, also dynamic surface reconstruction. Also, yeah, how to learn the correspondence. Okay, the correspondence is a classical, fundamental problem in geometry processing. Also, 3D object detection and high-level analysis. Yeah. Yeah. Okay. Yeah. Thank you. Yeah. This is my presentation. Yeah.
Okay. Thanks,